So our project was design of an injectable nanomaterial drug delivery system for optimized tissue regeneration. My name's Shri. My team members were Derek, Brianna, Elizabeth, Ryan, and Hunter. We did this with Dr. Yupeng Chang of the Department of Biomedical Engineering. So our project was aimed to aid pediatric growth plate fractures, which impede the growth and cause development problems and disabilities. Currently, the only method to solve this are surgery that is unreliable with a 15 and 38% success rate. Through Chen's lab, they were able to develop a minimally invasive procedure that includes proteins and nanotubes and hydrogels that inhibits angiogenesis and bone formation and improves cartilage regeneration. The objectives for the project were to develop an in vitro bone model to access injection through SolidWorks and 3D printing. Also, another aim was to develop a suitable hydrogel formulation to seal the wound and localize treatment. And this involved to identify the proper hydro material and methodologies involved. Constraints of both of these are, for one, the bone model being size. We need to be the size of a child's femur. The materials we were able to use to 3D print and the SolidWorks files. For hydrogel, constraints were time and dilation. I need to be within 1 to 5 minutes because that's the range for surgery. And body temperature, which needed to be, and temperature, which needed to be around body temperature. And the time of degradation, which needed to be by minimal to 2 weeks. And finally, needed to be biocompatible as it was going inside our body.
All right, now on to the alternative design section. The current design being utilized is a PLA model of a femur with a type 1 Salter-Harris fracture with no internal anatomy. PLA was used because it has similar material properties to real bones, such as stiffness, and in time, all the fracture types will be printed and tested on. Two types of hydroxyapatite adhesion were discussed, and we decided to go with dip coating. This method involves dipping models into a hydroxyapatite slurry, then letting them dry, leaving only hydroxyapatite on the model surface. Mixing hydroxyapatite with filament plastic, then extruding it was also discussed, and this would simulate bone better than dip coating. However, we didn't have access to the technology needed to do this, and there was a lot less literature available to support its effectiveness.
For the hydrogel design, we debated between agarose and alginate, testing them at varying concentrations between 1 and 3%. Alginate solidifies by addition of calcium ions, where the calcium present in the bone will solidify the hydrogel, whereas agarose solidifies by cooling. So as it cools within the body, it will solidify. Ultimately, we decided to go with dip coating as it is cheaper and more feasible. And for the agarose, for the hydrogel, we decided to go with agarose as gelation is temperature dependent and similar treatments have already been performed with agarose.
To start testing, we began by designing the bone model on SolidWorks. We did this by importing an STL that was made from a CT scan of a femur, and we added fracture type 1, which is a horizontal fracture spanning the entire growth plate. Once this was done, we printed it on a MakerBot Replicator Plus using black PLA filament and printing from the anterior side of the bone to the posterior side of the bone with supports and rafts that were removed afterwards. To test the hydroxyapatite coating, we decided to start on a small scale by using PLA cubes to test the adhesion, and a hydroxyapatite slurry was created by centrifuging the hydroxyapatite powder in the H2O mix. And then we dipped the cubes into it in 1, 2, and 3 coats. It appeared that with more coats, the covering became thicker but less uniform, and one coat had enough coverage to adequately mimic bone without any deformity. And we also applied shear forces to the coatings to see if any hydroxyapatite would come off, but no flaking was observed.
The third part of our testing involved agarose gelation time testing. The gelation results were obtained at 37 degrees Celsius. During testing, it was discovered that any concentration over 3% became too viscous to use. The lowest gelation occurred at 3% agarose, which was on average takes approximately 2 minutes to gel, which fits within the 1 to 5 minute time constraint. In summation, the limitation of the current system are that current practices remove bony bridges after it's formed, It's invasive and not very successful. The Chen Lab solution prevents bony bridge formation, is non-invasive, it localizes drug delivery, and promotes cartilage growth. For our project, it is to translate the animal model studies to methods of clinical uses by developing a bone model to test the injection system in hydrogel, along with developing an easy-to-use clinical injection system for clinical trials.
All right, so over the course of the design project, we came out with several prototypes, one of which being for the bone model and the other for the hydrogel. For the bone model, we created a 3D printed PLA model with the surface coating that was described earlier, using the one coat of hydroxyapatite that was found to be sufficient. Currently, we only model the type 1 Salter-Harris growth plate fracture. For the hydrogel, we use 3% agarose due to the gelation time being closer to the goal and the increased difficulty found with viscosity at higher concentrations. In future steps, we are going to print out the other fracture types, numbers 2 through 5 of the Salter-Harris classification. Coat the bone model with hydroxyapatite in further testing, and test the agarose gelation in the bone model. We'll also test the degradation time of agarose in body conditions in vitro, and develop an injection system that will heat the agarose so that it liquefies, mix all the treatment components together evenly, and fill the entire fracture site in the future.